I'm the technical manager with MultiXscale, and I will talk quite a bit about Easy and how it works, but I also wanted to start with giving a lightning overview of the MultiXscale project to kind of motivate things a little bit. So MultiXscale is a collaboration between scientific partners, which is from the CCAM nodes. So the CCAM network is more than 50 years old, and it's about scientists collaborating on advanced computational techniques and using those for important problems. So they are delivering 3 pilot use cases. And then on the technical side, then we have people from the Easy initiative who are providing technical expertise and who want to help to provide the tools that the scientists need and the application software that they need to be able to use that seamlessly across any hardware that they have available to them. And obviously Euro HPC is some of that hardware. And MultiXscale, what it actually targets to do is to improve the productivity of the domain scientists, the ones who are developing or using open source codes, to improve the performance of the codes that they use on Euro HPC hardware, and obviously that also implies beyond Euro HPC hardware. And then the portability of the codes as well, and to make sure that it's easy for scientists to transition from their laptop to a server, to perhaps they have access to cloud resources, and of course to HPC and Euro HPC in particular. The focus of MultiXscale is multi-scale modeling, and I'll show that because I'm going to talk about 3 pilot examples that highlight this, and then the leveraging the opportunities that Euro HPC offers to the domain. The idea ultimately is that we want to transition the community or accelerate the transition of the community to use the exascale resources that are available to them. So 3 pilot use cases that we have. One of those is batteries for sustainable energy. In particular, what we're interested in is supercapacitors, because they have potentially have superior power density to the traditional batteries, perhaps that we know now, lithium-ion batteries. The use case for these is interesting because while they are starting to appear in high-performance supercars, they're also very interesting for large transport as well. So for things like buses and trams and trains, because what happens with things like regenerative braking is that for large heavy objects like that, you generate an awful lot of energy in a very small period of time. And typically that can't be stored or all of that energy can't be stored by lithium-ion batteries, so it goes to waste. Supercapacitors are very interesting in this case because they can store that energy quickly and release that energy quickly for acceleration as well, so from like a standing start or something like that. But unfortunately, predicting materials that have enhanced performance for supercapacitors, that requires different scales and extremely large scales as well, right? Because you're interested in the large scale properties. One of the other pilots that we're interested in is a biomedical application. In particular, what we're looking at is the ultrasound process and creating an accurate digital twin for the ultrasound process. Many of you, or anyone who's had a child, is probably familiar with ultrasound, or even in the diagnostic capabilities, right? What ultrasound can do, and it's non-invasive, right? So it gives you diagnostic capabilities. But it also can be used for treatment, right? So this is kind of relatively new phenomenon where people are looking at ultrasound for treatment as well. And in the case where we have a digital twin, we get this opportunity to improve protocols, right? So to be able to do controlled testing and rational optimization of the parameters that are available to us for ultrasound, such as the frequency and the amplitude. So there's a lot of possibilities that open up when we have something like an accurate twin of this process. The final one is perhaps a bit more traditional in the sense that it's a design of helicopters for civil applications. In general, simulating something like a helicopter is a very complex task, right? We've got fluid flows around the helicopter body, and we've got lots of mechanical forces that are acting upon the helicopter itself. And then we have this coupling of the aerodynamic and the structural modeling at different resolutions, and this is extremely expensive when we're talking about high fidelity models of these things. And of course, we've got these large moving bodies, right? We've got the helicopter rotors as well, which complicates the whole thing. So in general, it's just a complex issue, a complex problem when it comes to simulation. Now, all of these scientific motivations, in the case of MultiXscale, we believe that they require also technical innovations. So each pilot is dealing with phenomena that manifest at different scales, multiple scales, That usually means that they're using lots of different methods at the same time. And that can mean also that they're using a variety of different software applications. So it's not just a single software application. It can be a workflow, or usually contains partially a workflow in these kinds of use cases, and coupling different applications together. So the challenge there is this, exactly that. It's this coupling, and making sure then that you don't lose access to large-scale resources when you couple codes together, right? So this can potentially come with a cost, and because the coupling doesn't necessarily scale between different application codes. So this is something that we're interested in. Of course, the large-scale resources that we're talking about in particular are the ones that we find, for free, which is great in Euro HPC. But having access to resources isn't enough. So for the case of the domain scientists, we want to get their entire workflows onto these machines, and we want to make it as easy as possible for them to transition, to use these machines and transition between the different kinds of resources and the different architectures that are available within Euro HPC. Now, unfortunately, scientific software is a different breed. So typically, or usually, it's not common that scientists are trained software engineers. It doesn't happen very frequently. And that's okay, right? Because their expertise is somewhere else, right? It's something very important. They do often need a lot of help to get software installed properly, particularly when we're talking about HPC systems, because there's a lot of peculiarities when it comes to HPC systems. So the standard packaging tools that you get, like with your operating system, they don't really suffice, right? We need to build from source, and we need to build from source because we care about performance. In the graph on the bottom left, we have GROMACS, right? Which is there's two different builds here. There's one, a generic build, which is great, right? Because it runs on multiple different architectures. You can take that binary and run it in lots of different places. But that portability comes with a cost, right? Unfortunately, if you have something like an Intel Cascade Lake system and you run that binary, but then you run the same code with an optimized version of that binary, specifically for that architecture, you'll get 70% speed up. So this portability with that initial binary comes at a great cost in terms of performance. And so basically, this is why we need to build from source when it comes to scientific software, because we need to take advantage of the hardware that we have access to. And that's it, right? So scientific software needs to be compiled for the system on which it will be used, because we care about performance. And this is complicated, right? This is a big problem, right? Because there's not enough collaboration going on in this space. The amount of software that's out there and available and used by scientists is exploding, right? And it's typically too much software for a single support team to handle. And then there's lots of different systems as well. So there's different CPUs, there's different operating systems, there's different accelerators, there's different interconnects. And all of these things, unfortunately, this spectrum of possibilities leads to different problems, right? So there are tools out there that help in this space. So the one that I contribute to is EasyBuild, but there are other options like SPAC, and there are more beyond that as well. But they're not really sufficient because they themselves require a learning curve from whoever is using them, whether that be the scientist or the site or whomever, right? And they still have problems. They're not the panacea for every kind of issue that can arise during a build process, because we have these different systems. So this leads in general to a lot of duplicate work, both across HPC sites and among scientists themselves, because a lot of scientists these days think that perhaps containers are a solution, right? And then they can manage an environment as containers. But then they're assuming all that work, right? All these issues that can arise from building things like containers, that becomes their problem. So this is also, Lisa, an awful lot of extra duplication if that expertise is not being shared. And in general, then we have lots of diverse software stacks and lots of different platforms, right? So we have, like, in the HPC space, we have somebody, for example, who might control their own environment completely, like all their apps and all their libraries. But then you might have central libraries, you have central applications that are available, and then people would use their own applications on top. On a desktop, obviously, the user is going to control everything there, assuming that they have that kind of rights. And then typically in the cloud, we're talking about running containers. So what we say here is that, the EC is to the rescue in this environment. So what do we do in EC? So EC is basically, what we do is provide, we take the host operating system, but we provide a compatibility layer on top. That compatibility layer basically acts like an operating system on top of the host operating system, but it's not a container. We'll come to a bit more in detail in that later. But basically, we have a compatibility layer, and we build that then for families of CPUs. So in the case of x86, you're talking about the Intel and ARM families, and then for ARM, then it's AR64, right? And also the plan is, of course, to expand that to include like RISC-V or anything else that might be out there. So on the software layer, that's the layer where we care about performance, okay? On the software layer, we have the different families, but then within those families, we have the specific CPU targets or instruction sets that we're interested in, right? So for Intel, that's Haswell and Skylake, and for AMD, then it's Zen 2, Zen 3, and obviously the new generations of things that are coming out as well. And then in the ARM case, then we obviously can provide generic, but we can also provide the optimized things for like Neoverse, N1 and V1, things like that we will see very soon. For example, in the Jupyter system that's coming in UIC. The beauty of EC is that you can take that approach and it can apply to HPC, where we see all these accelerators, where we see all these interconnects, and that can still work in that space, not losing any of those capabilities. But it can also work in the cloud, and it can also work for the users themselves on their laptop, in a virtual machine, on their desktop, wherever that might be, whatever they have access to, they can get the same environment with the same executables that will run optimized for the architecture that they have access to.